I am delighted to welcome the winner of the 2020 Unilever Colworth Prize, Dr. Manu Prakash from Stanford University. The prize, sponsored by Unilever's Safety and Environmental Assurance Centre, is awarded annually to an individual who has demonstrated outstanding contributions to translational microbiology. Dr. Prakash is known for his pioneering work in inventing high-tech tools using inexpensive materials, an endeavour he calls frugal science. His inventions may have been designed to address complicated problems, but their low cost and simple designs makes them accessible to everybody. I'm sure we will all enjoy his talk on frugal science, a practical guide to making science accessible to all.
Thanks for having me. I'm assuming you can all hear me. I'm going to share my screen. So it's 1 a.m. here in California. It's quite late, and instead of a room filled with colleagues and friends discussing and sharing science, I'm sitting in front of a computer in my kitchen talking to myself because I actually have no idea who all is listening. My name is Manu Prakash. I'm a faculty at Stanford. And maybe in the next 20-25 minutes, I just briefly want to share why it's so important to share science and why it's so important to share the experience of science. I think I got into science and because just of the joy and the number of questions it brings to me personally, that makes the lab kind of a scatterbrain. I'm incredibly humbled and happy. I get to work with just a phenomenal group of people, young students, scientists across the world, sharing our science. But instead of telling you about many of the discoveries that we've had the chance to make, many of the puzzles in biology that we are really excited about, I'm going to try to tell you a story about when I look out the window in the world that I see, what do I want for that world to have? So it's sort of an outward looking view, and it's challenging. And the reason it's challenging when I think about the world at large is just the sheer lack of healthcare resources that are broadly accessible to people around the world. When we look at our environmental context and the fact that majority of our environmental reserves are being polluted to an extent where the ocean is filled with all kinds of pollutants. When I look at the context of education and I think about the kinds of creative tools that students and kids around the world might have, it's fairly limited. This is a picture on the right that I took in Ghana, and it reminds me sometimes of, a roof does not make a learning environment to begin with. And actually, many of these challenges really have less to do with faraway regions from the world versus haves and have-nots. As a grand challenge, we often think about where is science done and who gets to do science. So I think instead of telling you about the scientific discoveries that we have made, I want to share a few minutes the challenge that exists in how to make science more accessible to everyone. This is a grand challenge, and I don't have to overemphasize this because the reason we're locked in our rooms is, you all know, we are in the middle of a pandemic and the kind of a disastrous situation that's unfolding around the world. Most of the problems that I describe are planetary scale. We need to measure biology, and especially microbiology, at the scale of the planet. That's truly when we can understand the power of the microscopic world and how it runs this planet. And we have to do this in an inclusive environment where we can call common citizens that share this planet with us as our collaborators, amateur scientists across the world, sharing the passion for science. How do you do that when I think about science, the first image that appears is of a lab? Could be a fairly well-equipped lab. And that's quite limiting because we have not had the chance to truly take science to every person on this planet and every place on this planet. This is not a new challenge. If you look back at the history of science, we faced challenges like this. One example of this was Operation Moonwatch. I don't know if some of you remember at the time when the Russians launched Sputnik. There was a fear associated with there was an unidentified object that's watching us, but nobody had the technology to observe the sky and identify where is this object, unless this object actually released its code and its location. That led astronomers to essentially start the world's largest citizen science program that's called Operation Moonwatch, with tens of thousands of people around the world every night looking at the sky. All of that was driven around with these little telescopes that you can see. And I love reading the sign around this specific version, which says, Mrs. Lloyd Eisenhower, housewife volunteer, sought Sputnik 2. And it's these sets of communities that actually identified and detected the first rounds of Sputnik. And when I think about of our healthcare around the world and billions of people receiving healthcare, I think about a citizen science program. In fact, you could argue that our community healthcare worker program is the world's largest citizen science program, primarily run by individuals like here from Liberia, who might have a 8th grade education in a formal setting, but is engaged in delivering healthcare and diagnostic services, and I would say the highest level of microbiology service that is possible in a rough environment like this around the world. The reason we don't talk about Ebola as often is because of individuals like her who put themselves in the front line getting and detecting infectious diseases in places where they first occur. As a lab, we have thought about this and often asked ourselves a question: how could we enable individuals to really do their best science that could fit in that backpack, that could truly deliver microbiology, but at the grassroots? So this is what really the talk is about. In the context of diagnostics of diseases, you can think of it as being able to diagnose diseases, except to be able to do that under a tree. And that phrase comes from the fact that I spent a lot of time in Uganda, and one time I met a pathologist who pointed out, if you're excited about bringing technologies, bring them to me when they work under a tree, because that is the harsh reality of literally 2 billion people and how they access healthcare. And I'll get back to that in the very end again. But we have had the chance to both build and design tools to both democratize access to science, to diagnostics, and more recently also ecosystem surveillance, because it's equally important to be thinking about the pathogens that nobody's talking about, not just the pathogens that are in the heart and center of the conversations that we have right now. There's a number of tools that we have released. Today, I'll end up just focusing briefly on the optics, but we've been able to build molecular surveillance tools to map viruses in mosquitoes, study pathogens like schistosomiasis, also invent completely new ways of doing surveillance and sample processing in the field. But for today's talk, I'll focus mostly on microscopy and the role of microscopy in public science. So just on the context of microbes and mosquitoes, this is very recent work looking at to be able to do virology of mosquito bites, but at a single bite level. I know this is the era of single cell sequencing and single cell genomics. We asked ourselves, why can't we do single bite omics? And that led us to develop a platform which is called VectorChip, which allows us, if you see this video, what you're watching are single mosquitoes that I've stained with fluorescein. But every single bite, they release a tiny drop of saliva. And using that single salivary drop, as you can see, we can identify and literally count the number of active viral particles in this single bite. We do this with a clever microfluidic trick that allows us to essentially do surveillance of mosquitoes without ever catching them. And in very, very brief, I'm not going to give a technical talk today. We can utilize a tool like this to count how many pathogens are there in a single bite, but also identify the species of mosquitoes that's biting, allowing us to identify that mosquito and hence make a connection with transmission without ever catching a mosquito. We're very excited about this tool because we will be able to really deploy this at scale, thinking about searching for new viruses that might be floating around that have not established themselves in human hosts. Switching to microscopy, there is a number of tools. I'll briefly describe 3 tools, all the way from FoldScopes on the left, Plankton Scope in the middle, and Octopi, which is a recent tool that we have developed for malaria diagnostics. The challenge with Plankton Scope is very, very simple, which is many of you already know microbes in the ocean are important, but studying the ocean is extremely expensive. If you have followed through the David Attenborough research vessel, or the Boaty McBoatface, for that matter, one of the challenges that you realize if thinking about research vessels is it can cost upwards of $50,000 to $60,000 a single day to spend in the ocean, sampling the ocean. And we asked ourselves, how could we flip that around and really enable sailors around the world? There are 15,000 or more sailboats, recreational sailboats, sailing across the ocean in far greater and far heterogeneous and randomly sampled locations in the ocean than research vessels. And we started building low-cost tools to enable a sailor to really be able to sample the ocean. That led to Plankton Scope. It's an automated microscope that any one of you can build. It costs around $200 in parts that you can put together. But very powerfully, it allows us to collect this type of data. What you're looking at, this is data collected in the middle of the ocean in the Atlantic in a bloom that might occur. And of course, this is a high-speed imaging tool that allows us to collect this type of data, map that, understand using machine learning, speciate it, and really build a true map of, I've often been thinking about them as ecograms. So this is an example of this tool. As you can see, this is essentially in a lake in India with a fishing community that's focused on engaging in sampling the planktonic diversity in a traditional fishing village. And this is the type of data that comes out of that 15 minutes of sampling. And what I meant by ecogram, many of these snapshots, we don't even know what these microbes are, but we know their presence, we can classify them, and we can start to understand with very minimum tools, what are the ecological snapshots of these. The paper is published. Many people have started building these tools across the world. If any of you are interested, you can look at planktonscope.org. So that's the website. And I'm going to skip this, but tell you a little bit about malaria. Another tool that we've been working on has been automated imaging on detection of malaria. And the challenge associated with malaria diagnosis, if any of you have spent time doing microscopy in the field, you realize it can take upward of half an hour or so to detect a negative slide. The kinds of stains that we've been using to identify malaria are still literally the Giemsa stain that was defined by von Gimsa in 1904. And in fact, we image more than 200 million slides per year, but we really don't have any data to show for that other than yes, no answers. We started thinking about this and we built a modular automated microscope that costs roughly around $100 that anybody can build. This is completely open source, but it allows us to really do automated imaging in the field settings. And one of the important aspects of this is, I'll just play this video. We've been able to implement spectroscopy and not just microscopy, implying we are not just looking at the shape or form of these parasites, but also the spectra of lights that they're emitting. And using that spectral resolution, we've been able to identify malaria parasites at very low magnification. So what you're looking at is a tool that runs through a battery power pack, and it's capable of essentially imaging 15 million cells in 5 minutes and identify and classify and then provide a diagnostics framework in a completely automated fashion. This is that same tool implemented in Kalahandi, one of the highest regions for malaria parasites. We're starting large-scale validation studies for these tools. And again, much of this is online and accessible. We called it Octopi because it's a fairly versatile tool in microbiology. This is the example of what I meant by that spectral shift. So this is the data collected in the field. On the left, you can see the tool is identifying all the platelets, and you can see they're all in blue, while on the right, the tool is identifying all the malaria parasites in a completely automated fashion. And you can see that the color of those is green. And what we're really using are dyes that differentiate based on the DNA to RNA ratio in a cell, a spectral shift associated with it, which we can use to identify. And one of the plans that we have to not only open source, but we have formed a consortium very much inspired by Fred Whipple and Operation Moonwatch, is an army of robotic microscopes essentially watching pathogens, very specifically focused on malaria, but also opening it up to a broader group of pathogens. And you can see that's Ethan in Uganda holding one of these microscopes in their hand, and we're starting to scale this to around 100 instruments first. Lastly, I think the thing that I want to really talk about and mention is how do you scale these ideas, and how do you really bring curiosity to people beyond very specific applications? It's been almost 9 years. I started thinking about what does it mean to be a pencil of microscopy that led to this tool called FoldScope. And it's been a while, and one of the challenges we wanted to think about is how could you build and design a tool that could give you could watch a single bacteria, but it should be less than $1. And over the last 7 to 8 years of deploying this tool around the world, I've learned many lessons. One of them is, although I was thinking I was building scientific tools, I later realized that I was building scientific communities. These are pictures from around the world. At this point, we have scaled and shipped roughly 1.4 million microscopes. And that encompasses more than 158 countries. This is a fairly old map. It covers all regions of the world. And what is very powerful is majority of these 1.4 million people are for the very first time being introduced to the microscopic world. So I want you to truly imagine the first day that you look through a microscope. Think about that same day and sharing that moment with a larger group of people. These individuals might not look like scientists like you and I. This, for example, is a picture from a farming program for training traditional farmers in identifying pathogens in their plants. And it's being run in Chhattisgarh with very, very limited resources. Another example is our partnership with the government in India to really scale this tool to bring this to the masses. So at this point, we have developed individual program with roughly around 50,000 workshops being run across the world, thousands of volunteers engaged, and very importantly, sharing data on a common platform that allows a broader world to essentially look and explore these types of ideas. Here is another example. There are thousands of examples like this, but I chose this because of a conflict zone. This is a FoldScope club in Iraq. The club formed 2 months after the Iraq war ended. And this is Muhammad literally inspiring and taking a generation of kids who, without him, might have actually never been introduced to the world of science, and how much they have lost in the kinds of atrocities that happened in the war itself. One of the things that I want to end with is, I was preparing for this talk, and then a few days later, we are seeing one of the worst cases of this pandemic. We've been working on this issues of the pandemic for the last 9 to 10 months, building lots of tools. I've often thought about this, that the pandemic inspires us to build and design tools, take advantage of using a crisis to bring new tools to people. But we've released many tools, all the way from diagnostics to ventilators to mask manufacturing capabilities, and most importantly, home diagnostic tools and molecular tools. But one of the things that I have to share, which is a sobering moment for us at this very moment in the history of this pandemic, is what's happening currently in India. It's been just an absolute tragedy. I grew up in India, and I've followed through the pandemic throughout, and suddenly what we find ourselves is not just a problem in India. This is a tweet that I picked from a friend of mine, Madhu, who's just describing what's starting to unfold in all of South Asia. If we don't address these sets of challenges in the broadest set of sense, by sharing science as broadly as possible, by sharing vaccines, by sharing solutions, realizing the fact that a pandemic is a global problem that requires global coordinated solutions. And if we as scientists don't speak up on engaging the politicians and the governments to do something about it, I think the history will not be very kind to us. The history would talk about the most important advances in vaccines happening because of the pandemic, which would be a triumph for science. But the history would also talk about the tragedy of how an incredible output of these scientific tools was not broadly shared because of patents or because of greed or because of political motivations, to really get us into what I've been thinking about, a forever pandemic, a pandemic that never goes away, keeps mutating, and harshly put, really affects the poorest of the poor. And I think this is the harsh reality that we find ourselves in, and is a sobering moment, as all of us look at the sets of pictures that are coming out of India. It really breaks my heart. One of the things that, rather than feeling helpless, we've started an organization called India Covid SOS, which is a group of 500 clinicians, doctors, scientists across the world trying to support scientists and physicians and folks that are fighting the pandemic in India and South Asia. And I think if any of you is interested in engaging, we could truly use your help. What's unfolding is truly a tsunami. And I think I couldn't find better partners than many of you who have the kind of expertise that we really need globally to fight this pandemic. I'm going to end here with just a reflection, which is associated with, I've been known to share scientific tools, and it gives me great joy to say that we have built the world's largest amateur microscopy community. There are more people using microscopes because of some of the things that we have done than in the previous history. But this picture is also sobering. This is a picture that a friend of mine sent me from a village in Vellore, in a program where FoldScopes are used regularly in classrooms. And you could see the palpable excitement these kids have for science. But you also realize this is a drop in the ocean. The fact that there are 2 billion kids on this planet, and you have 1 billion kids that live below a poverty line and hence will never have access to the kind of tools for scientific creativity. And I'm not talking about having access to the internet and being able to look up what an E. coli is. I'm talking about the capacity to watch an E. coli dance in front of your eyes. And as scientists, we all know without that capacity of experience and aha moment, we will never be able to transform our thinking, never be able to bring scientific literacy to be a human right. And frankly, if we don't share that scientific knowledge and that scientific tools, we will always be fighting the fact that a significant portion of the world might not even believe in germ theory because they can't see those germs to begin with. If you realize what happened in the anti-masking movements, where the fact that people don't find it worthwhile to wear a mask in such a heightened state of a pandemic, is really the fact that although scientific knowledge has advanced incredibly, uh, the experience of science has not been shared. So I think I urge all of you to think, how could you bring your science to people? And I think it would make it for a better world. Thank you so much for listening.
So thank you, Dr. Manu Prakash, for this wonderful talk. And I hope you don't mind if I switch back and forth between Manu and Prakash. And first of all, let me congratulate you on winning this Unilever Colworth Prize. This one is prestigious prizes that Microbiology Society gives out annually. I must say that your talk is always very, very um, exciting and inspiring. I think inspiring is the probably the best word to describe your presentation. I still remember vividly the first time I heard you at the American Society of Microbiology conference, and thanks for accepting our nomination and the award. So let's get a little bit into what got you started on this journey, because I think for me that's most exciting. You are in a very prestigious institution. You have your own commitment, but yet you do things that is completely outside the realm of your expectations. So can you talk to us about it?
Yeah, I mean, first of all, thank you so much. I'm absolutely honored. I wish we could have all met in person and shared insights, but it's remarkable as a society, and especially the value of sharing the gift and privilege that we have of curiosity with the broadest group of people. So I'm really humbled by this, and thank you so much for this honor. Uh, I think for me, growing up and who I became as a scientist, the idea of sharing and the access to science is an integral part of the fundamental discoveries that we make, both as a lab. Uh, I do this work not in the context of outreach versus what I'm pursuing as a question. Living systems have inhabited this planet for a very long while. And if we truly mean to understand them in their full glory, we have to have the capacity to observe them in their native habitats around the world. And what better way than to empower people to actually engage and observe with us? So I think I have made fundamental discoveries, literally finding an object and a microbe, literally looking only through my microscope, my FoldScope. And my hope often enough is that that sense of joy and discovery, if we can share that in the broadest group of people, that begins a lifetime of commitment to science for someone else. So to me, this is not either or. It really is folded very intricately in how I think and how I am as a scientist. And I'm actually very happy in the last decade or so, we have committed to deploying these tools in the community. The communities have become far more powerful and important than the tools that we have deployed, because these communities have been able to tackle problems that I just myself wasn't even aware of, forget about having the capacity to work on. So, I think it just is a joyful moment for me, and our work is not done. We have a long way to go, but on the other hand, it is who I am as a person.
But you make when you started in this journey early in your career, um, there was no financial support. There is no, most people will look at you, here comes the, does he have a crazy ideas? And yet you were able to surpass those things. What made it possible for you to deal with so many naysayers in your journey to this point?
Yeah, I think you touch on a nerve there. uh, uh, I'm sitting here just reading two naysayers a few minutes ago on something. Science is, we do science because of our internal compass. And sometimes it's essential to be aligned with that internal compass. Um, you're right, we had an extremely difficult time trying to be able to fund a project like this, especially because just going beyond writing papers, which was not the goal of this, we wanted to deploy this tool broadly. And I remember explicitly one day in the lab, sharing with the lab that, we will build and deploy 50,000 of these around the world to anybody who asks for. And I remember reaching out to every possible organization I could, and just, it didn't click. Somehow, this idea that deployment and sharing technology and capacity is an equally important part of the work of invention of technology. I'm very fortunate. I accidentally met a remarkable individual at Moore Foundation, and she understood both our passion and our desire to do this and supported the first round of the work. But literally, that was after 15, 20 organizations that you would typically take ideas like this to. I explicitly remember we spent to ship those 50,000 microscopes, we spent 70 to $80,000 just shipping instruments to Sudan and remote parts of India and remote rural US. And it was really labor of love. I really have to say this. We are at this point where we have deployed roughly 1.5 million FoldScopes,
Wow.
and it's become one of the largest microscopy community in the world. But on the other hand, the beginnings were definitely far rougher. And I often think about, what if I had decided to give up? What if I had moved on? I work on many broad range of technologies, but I think the lessons in implementation science, which is an integral part of discovery and sharing that joy. There are often these moments that you make decisions that you don't comprehend yourself. And I think one of those decisions was deploying these tools.
Oh, that's a excellent decision, I must say. Personally, I have moved on from certain things, and looking back, and I think, oh, why did I do that? So that needs a certain amount of grit to stay on this course. And obviously, at the end, you saw the fruit of your labor, and these folder scopes are amazing. And I think there is a lot more to do. There are more people can be reached, but I think they also need to have interest, right? Um, I want to address one other comment you made, and that has been bothering me a little bit. So the thing that you mentioned earlier was, you need to work with the people's curiosity. I often find this younger students, the students we get these days, seem to lack curiosity. Somewhere along the way, they lost the sense of, you know, to be curious about everything. You know, I'm curious about everything. So where does that happen, and why there seems to be a generation who is more interested in doing less curious things? And do you want to speak to that?
Yeah, I think it's a tough question. I would actually argue that uh, we don't lose our curiosity. It's suppressed by the system in many ways. And individuals, human race as a whole, we're born curious. We are born to ask questions. We're born to taste, feel, smell every possible thing. Uh, and the way and what we call education and how we structure education has a lot to do with what is allowed and what is not allowed.
Right.
I grew up in an environment where I didn't know the definition of a scientist. It's not as if I was looking to be something. uh, I was pursuing questions that bothered me. And I think this is fundamental to the spirit of sharing scientific tools as broadly as possible rather than sharing knowledge, which at this point is free. I mean, anybody could Google about a name of a microbe. If you haven't come face to face with a microbe before, which I would say majority of the planet has not, although our life runs because of microbes and the life shuts down because of microbes, as
Hope so.
we are facing right now, how is it that this capacity to see and observe and feel is not a fundamental part of our daily lives? Why are we not having, why are microscopes not on dinner tables? That is a question I ask myself every day, and I'm actually quite serious about it. I've felt
Yes.
often enough that a direct connection with the living world at the smallest length scales and the largest length scales allows people to flourish in their own sets of capacities. And I think I would argue curiosity in today's day and world is a privilege. And I say this sort of with a heavy heart because, as an academic, I am allowed to be curious because of taxpayers' money and because people fund what I do and questions that I ask that may or may not have relevance to their daily lives. But as a society as a whole, we value curiosity. But we need to enable and share that privilege with the broadest group of people. And I think the kind of evaluation based culture we have in education, which is so early on that you need to be right, is so damaging in many ways because
Right.
then students can learn to be right, but they might forget how to ask questions. So I would
Yes.
much rather live in a world where we value the capacity to ask good questions rather than be right. And I think this is a long road. Many communities and people have made commitments to really overhauling education. If you look at the sustainability goals, it's a very long road, and I wish from an investment perspective much larger investments were made in not just providing knowledge to people. I think tremendous amount of information and content is being created,
Mhm.
but you turn students into consumers, and I would rather have them be creators themselves.
Yeah.
So I'm optimistic about this. I don't feel any, you know, I what I have seen so far, I can tell you just remarkable insights in young individuals when they were given a chance to explore. And I think we have to be honest about exploration is unknown and you can't grade it. You can't, you really have to let people thrive and give them the time and capacity that they need. So, my hope is the dialogue will change.
Mhm.
uh, Universities across the world, schools across the world, scientists across the world can do something about it. It's not as if we we built this system, so we
Right.
can
No,
tear it down
absolutely.
and we can build it again.
I agree with you. You know, I love when the experiments fail, when the
Mhm.
students come and they say, "Oh, my experiment failed," and I was like, "That's great, right? Now we
Yeah.
can ask why."
Yeah.
And where did we go wrong and how do we fix it? So
Yeah.
I when the students come to me and say, oh, it wasn't as expected, I said, that's fantastic. I don't want to know the answers as expected, then we're not asking the right questions.
Yeah.
And asking question is such an important thing. And I, even in the world of, computer and Google, even with all the information at your hand, at your fingertips, if you don't ask the right question, you're not going to get the answer. And I think we have to really teach people how to ask questions. Thank you. On behalf of the Microbiology Society, I thank you, Dr. Manu Prakash, and wish you all the very best in everything you do. And please stay in touch with the society and with me, of course. Thank you.
Bye, everyone.